Good afternoon. Welcome to this Open University STEM Faculty Ask the Expert session on COVID vaccines. I'm Rachel McMullen. I'm a senior lecturer at the Open University, and I'm going to be your host for the session today. I'm joined today by two experts from the School of Life, Health and Chemical Sciences at the Open University. Dr. John Golding, who's going to be telling us about treatments for COVID, and also Professor David Mail, who's going to be talking to us about COVID vaccines.
Hello.
So the way the session's going to run today is that each of our experts will be giving us a short introduction to their subject. And when they finish speaking, there's going to be an opportunity for you to put your questions to them. So if you have any questions for our experts today, you can submit them to us via the chat, or you can use the email address stem-news@open.ac.uk. So to get us started today, I'm going to hand over now to John to just tell us a bit more about approaches to treating COVID. Over to you, John.
That's great. Thanks very much, Rachel, for that introduction. I hope everybody can see the slides. Can you see them, Rachel?
Yeah,
I assume that's a yes. Right. Okay. So I'm going to be talking about current and upcoming drug approaches to treating COVID-19. But first, a little bit of scene setting. So in any normal year, and this is 2019, I've got data for here, the unfortunate truth is that there are around about 56 million people that die in any one year. And of those, around about 7.8 million died due to infectious diseases in 2019. Diseases such as tuberculosis, gut diseases, HIV/AIDS, malaria. The rest of the deaths here are due to things like cardiovascular disease, cancer, diabetes, things like that. So for some context, that's what we expect to see just about every year. During the course of the past 12 months, there have been 2.5 million deaths due to COVID-19. That's basically the equivalent of all the deaths due to HIV, malaria, and other communicable diseases added together. And to further help you get your head around what we're talking here, if you can imagine the total populations of Edinburgh, Cardiff, Belfast, Birmingham, and Reading, all of those cities dead. So that's a hell of a lot of people. So I'm going to be talking about the drugs that can be used to help prevent or try and make it easier the symptoms of COVID-19. This little cartoon shows in gray a cell membrane. This could be one of your cells. The inside of the cell is at the bottom. The outside of the cell is at the top. There's this horrible coronavirus, and it comes along and it happens to stick to one of the proteins on the surface of the cell. So I've got several proteins here, some of them on the surface, some of them that go all the way through. And it happens to stick to and lock on to one called ACE2, which is an enzyme that normally is involved in processing a protein called angiotensin. But it just happens that the spike protein of the virus sticks to that particular protein. When it sticks onto ACE2, there are a couple of other proteins that come into play. There are two enzymes. There's this very eloquently named TMPRSS2 that cleaves the spike protein, changes its conformation, and lets it fuse with the cell. We've also got another enzyme called furin, which does a very similar job, and it cleaves the spike. The ability of coronaviruses to be cleaved by furin is actually quite recent. We first saw that with the SARS virus, and also now the coronavirus, COVID-19, is also using that as a way to help get into cells. Finally, there's this receptor called CD147. This has been claimed to be a receptor for the coronavirus. However, there was another piece of research that was done a bit more recently where they completely knocked it out deleted it completely from cells, and it had absolutely no effect at all on whether the virus got into the cells or not. So the virus may stick to it, but whether it actually has any role in getting the virus inside the cell is very disputed. Anyway, so once the spike protein has been cleaved by these enzymes, then that the virus membrane fuses with the host membrane, and the virus RNA and viral proteins get inside the cell. So what can we do about that? So there are several ways that we can try and inhibit that. We can work on trying to block the virus itself. So up on the top here, basically we are coming up with drugs that smother the virus and stop it from being able to attach to the cell in the first place. So the first obvious one would be a soluble version of ACE2. So normally that's anchored into the membrane. If you've got a soluble version of that, that will just block all of these spike proteins and stop it from binding to the ACE2 that's actually on the membrane. Similarly, you could come along with antibodies that recognize the spike protein. There are two that have been trialed at the moment, showing quite a lot of success actually. Those will smother and block the spike protein. Heparin, quite a well-known and well-used molecule, that also partially smothers the spike protein. And then finally, we've got this EK1 peptide, which is a peptide that comes along and it will bind to the spike as it's in the process of being cleaved. So it doesn't bind to it normally, but once it starts to get cleaved by these enzymes, then this will gum up the spike, and that prevents fusion. So those are the things that currently can be done to the virus itself. Down on the cell membrane, this cluster of proteins here, we could do something very similar in terms of blocking by bringing along a small peptide derived from the receptor binding domain of the spike protein. So we are effectively taking a small piece of the spike and using that to smother ACE2, and then it doesn't leave any other free ACE2 around for the virus to attach to. In a similar way, there's this antibody that will smother the CD147 and stop virus sticking to that. And then there are a couple of drugs that will inhibit the enzymes that can cleave the virus and allow it to fuse with the membrane. So that's what's in the arsenal as far as stopping membrane fusion from happening. There is another way that viruses can get into cells. This is an endosomal route. So what happens with that is that the cell membrane invaginates, and the virus goes into a little pocket, a little packet of membrane that breaks off the cell, breaks off the surface of the cell and goes into the interior of the cell. Now, of course, that then has to break open to allow all the contents of the virus to go in. But what usually happens is a bit of a kind of a disinfection cycle that happens to material that goes into endosomes. Lots of stuff goes into endosomes, but some viruses have found ways to do that as well. And what happens is that, first of all, acid is pumped into inside of these endosomes. There's a channel, an ATPase, that pumps in protons to acidify it. So the whole thing becomes acidified. We've got another protein here called a 2-pore channel that pumps calcium out of the endosome. And we've got an enzyme cathepsin, which is present in here and basically starts to degrade whatever is inside. And then that will pop open and allow things to come out. Usually that would be enough to destroy anything that's inside those endosomes, but quite a few viruses have learned to well, they've managed to put a protective coating around themselves, and they can survive those rather harsh conditions, and then they get released into the cell. So by either method, either by membrane fusion or by the endosomal route, you end up with viral RNA inside the cell, and also some viral proteins, of which this one is one of the most important ones, is our viral RNA polymerase. That does something that never happens in our bodies. That turns RNA back into RNA. So this makes new viral RNA. The rule in our bodies is usually that RNA gets turned into protein. So this is a very unusual enzyme that is used by this type of virus to make more of its viral RNA. What can we do to block all of these things? Well, we've got quite a lot of stuff that we can use in our arsenal to block this. The first one of these viral RNA polymerases, there's nothing like that in the human body. So we can come along with some unusual drugs, remdesivir and lopinavir, that will block this polymerase and stop new viral RNA being produced. We could come in and shut down some of these channels, baflamycin, tetranidine. These are rather toxic. You wouldn't really want to be trying these as drugs. This one will block the enzyme cathepsin. There's something called aplimod that helps to prevent this sort of maturation process from this stage to this stage. Hydroxychloroquine, lots of you have probably heard about hydroxychloroquine. What that does is it gets inside the endosomes. It's quite basic, and it buffers the endosome. It gets rid of all the acid. So the inside of the endosome doesn't get as acidic as it would otherwise do. And then the endosome never splits open. And up here, we've got drugs that actually stop endocytosis from happening, and good old interferon, which David may be talking about, which is a cytokine released whenever our cells are being infected with viruses, and that instructs the cell to destroy viruses. So we've got all of these different things going on that should hopefully, the end result is to try and get rid of that viral RNA and stop the virus from replicating. There are other drugs available that I haven't mentioned yet. So what things like dexamethasone, which is an anti-inflammatory drug. This has shown great promise in a small proportion of patients. So there are some patients in which they have dangerous levels of inflammation due to COVID-19, and dexamethasone can prevent deaths in up to about 35% of that group. But it's not just anti-inflammatory per se. So other anti-inflammatories, non-steroidal anti-inflammatories, they don't seem to be effective in the same way that dexamethasone is. And in fact, if you take ibuprofen, that can actually make things worse. So it's not necessarily just anti-inflammatory. There's something else that dexamethasone is doing. So there's probably some other mechanism involved in that. And then finally here, we've got antibodies that block the effects of two interleukins, interleukin 1 and interleukin 6. Both of those, they often get massively increased when you've got any kind of infection, but especially infections with COVID-19. Antibodies against these two cytokines have been tried. Neither of them have had any effect on death due to COVID-19. However, the interleukin 6 antibody does seem to reduce the severity of lung disease. So patients taking that with lung disease have spent less time in hospital because of that. And that just brings me to the slightly broader point that there really are so many drugs, potential drugs to research. So how do you go about choosing what's going to be a winner, and how do you avoid just getting on a bandwagon that everybody else seems to be getting on? So to evidence that a little bit, what I've got here is a bar chart showing you the number of publications in any month. So these are clinical publications for COVID-19 using different drugs. So the ones I've selected here are drugs like hydroxychloroquine, that's the blue bars, interferon, remdesivir, heparin, and dexamethasone. And you can see some trends happening in here. So the first obvious trend is that the amount of publications for nearly all of these drugs increased in the early months of 2020 to a peak in the late summer, and then kind of the publications tend to dwindle away. Remembering that these publications are at least a couple of months behind when the work was actually done, because it takes time to do this stuff and write it up. But there is one here that really leads the way in terms of publications, and that's hydroxychloroquine. Everybody wanted to be doing research on hydroxychloroquine. Why did they want to do that? it may have had something to do with this event that happened back in early March when President Trump promoted hydroxychloroquine to the world based on very, very limited data out of a French laboratory down in Marseille that has since been somewhat discredited. When that happened, the whole world exploded into wanting to do work on hydroxychloroquine. It just went off the shelves. You couldn't get hold of the stuff. It is used as an anti-malarial as well. So it just disappeared. Everybody was taking it that could get hold of it. That turns out to be a little bit of a mistake to take that kind of route. So I've got a table here that shows you all the various clinical trials that have been done for some of these drugs. And I just want to point out that right up at the top of the table, I've got 2 trials that looked at hydroxychloroquine. Both of them reported their results in February of this year. One was done by the World Health Organization, another one was a recovery trial, which is a much larger trial. In both of those trials, the proportion of deaths with the drug compared to people that didn't take the drug is higher when taking hydroxychloroquine. So in this case, with the WHO trial, 11% of people were dying that were taking hydroxychloroquine, whereas only 9% of people were dying that didn't take hydroxychloroquine. Okay, those differences aren't significant, but there's definitely a trend in there. And in fact, with the recovery trial, the larger trial with thousands of people involved in it, they stopped that part of the trial because people taking hydroxychloroquine under those circumstances were often dying with heart problems due to the hydroxychloroquine. So don't take hydroxychloroquine is basically the take-home message from that. Another one that's interesting here is remdesivir. So this is this antiviral that blocks the RNA polymerase. There was an initial trial published by the American National Institutes of Health back in November 2020. Fairly limited numbers of people, only 500 or so people. And that showed a really big apparent effect. So it basically halved the number of people that were dying. If you were taking that drug, if you're taking remdesivir on that trial, about 6% of people would die compared to about 11 to 12% of people that weren't taking it. So it halved the number of people. It was significant, p-value here very low. However, I just want to mention this value here, effect size. Effect size is a measure of the magnitude of the effect. So it's possible to have an effect that is very, very significant, but actually the difference between those groups is actually minuscule. It could be 0.1% that's changed, but it's highly significant. Everybody quotes the significance value. Very, very few people bother to look at the effect size. And in fact, none of these trials did. So I had to go and look at the data and actually do those calculations for myself. And the larger the effect size, the bigger the effect, kind of obviously there. But even with this NIH remdesivir trial, the effect size was really quite small. So not that great. However, on the basis of this trial, loads of governments, including the UK government, went up and bought up all the remdesivir that they could get hold of, and that has become the standard of care. Again, that was slightly premature because this February in 2021, the WHO released the data on a much larger trial that they did, the Solidarity trial, where they had about 5 times more patients than the NIH trial. That trial showed almost no effect of taking remdesivir. You had 10.9% people that died when taking remdesivir against 11.2%. That isn't significant, very low effect. Another antiviral drug, lopinavir, no change at all, whether you take that or not. Interferon, not significant, but there's a tendency for that to go in the opposite direction. So you're slightly worse off taking interferon than you are if you're not. Heparin is actually does actually show a trend towards being quite good, but the effect isn't significant. And dexamethasone, that does seem to show an effect. It's not that big, but it is significant, and that is often the standard of care for these people. So there's a little bit of a warning in here that people should really be looking at the results of clinical trials, and they should need to be quite large clinical trials before going off and doing things. And I can understand why governments went off on the basis of this NIH trial and bought up all the remdesivir they could get hold of, because at the time, there's a very rapidly moving disease, horrible disease progression. We needed any ammunition we could get, but it perhaps doesn't do what it says on the tin. So just reiterating that, these are the current NHS treatment guidelines, is to take remdesivir for 5 days, even though it may or may not work. Dexamethasone does work. You're supposed to be taking that for at least 7 days. And they also regularly turn the patient onto their stomach to help drain the lungs in serious cases. That compares similarly with what the Americans do. So the current NIH guidelines, if you are in hospital, so it starts off with varying severity. So if you start off in hospital, but you don't need oxygen, then there's not a lot they do for you. You might be getting remdesivir, but you won't be getting anything else. You won't be getting dexamethasone. You won't be getting any other corticosteroids. Once you start getting onto oxygen, then yes, just like the UK, you're given remdesivir and dexamethasone. If things get more serious and you need a higher rate of oxygen, then again, dexamethasone and remdesivir is what are given. Once it gets very, very serious and you need invasive mechanical ventilation, something like an ECMO machine, all that they can offer you really is dexamethasone, and that does seem to help. So everything here seems to be focused on drugs that are given when it's starting to get almost too late. However, there is a glimmer of hope, because just last month, at the end of last month, if you remember me talking at the start about these antibodies that can block the spike protein of the virus, that's been approved. That's had emergency approval by the NIH, and that is now being used in outpatients or patients with mild to moderate symptoms before they even start getting into this hospital kind of spiral down. And we're really hoping that that will prevent people falling down this route. So I look forward to seeing how that works out. So why don't these other drugs seem to work? They all work in a dish, otherwise they wouldn't be tried on people. The problem is that COVID is such a horrible disease, and patients deteriorate so rapidly, often within the case of hours. And some of them just present at hospital too late for many of these drugs to work. Remember, a lot of these drugs are aimed at stopping the virus getting into you in the first place and slowing down the formation of new virus. But often by the time people present, that's, the horse has bolted, that's already all happened. And the other point I would like to make is that we do always need to have large scale and objective testing, and it takes time to do this. And if you don't do that, then you have people doing knee-jerk reactions, drinking bleach because people suggested that, hey, you can use bleach to clean surfaces, so why don't you drink the stuff? And the same kind of story here. This is from the Centers for Disease Control in America, where they did a survey of 502 adults. That was back in May last year. And you can read the data for yourself, but of those, 4% admitted to drinking bleach to try and cure themselves. And I think that's all I really wanted to say about that. So I'm going to stop sharing my screen and hand over to David. I hope everybody heard that, and I wasn't just talking to myself.
Yes, we all heard that, John. That's very interesting. Thank you. I presume that we're going to sort of carry on with a presentation here. So I'm going to talk a little bit about vaccines and variants, and then at the end of that, I guess we'll take some questions. So I'm going to start by sharing out my screen for you, which I hope you'll be able to see. if I put this up for a slideshow, starting from the beginning. Okay, can you see a slide with vaccines and variants on it?
Yes, I can.
Okay, good. Okay, so I suppose the key question that a lot of people are asking is how effective our vaccines are and whether the variants that are arising all the time around the world may be able to evade the vaccines or produce more serious infections. And this slide here demonstrates some of the ways that we have traditionally produced vaccines against viruses. So if our virus is up here, one way that people have produced vaccines is to attenuate the virus so that it is less dangerous, less pathological, but is still capable of immunizing people. Another way is to inactivate the virus. A third way is to take components of the virus. For example, if we're talking about COVID here, we could take the spike protein. And then there are two of the newer ways of producing vaccines, which interestingly have come through more quickly than the traditional ways. One of them is to take the DNA from the virus, or the RNA from the virus in the case of COVID, and to place it inside a vector. And then that vector carries the RNA into cells of the body where it produces the spike protein or the other protein, which effectively fools the body into thinking that there is an infection. And finally, and actually interestingly, surprisingly, the way that seems to have been most successful early are the use of the DNA, or in this case, RNA vaccines, where the RNA which produces or codes for the spike protein is directly introduced into the body, and the cells of the body take it up, and then the immune response develops against, in this case, the spike protein. Now, it is quite staggering to me how many successful vaccines we have developed over the last year at extraordinary speed. You'll be probably familiar with the Pfizer vaccine and the Moderna vaccines, which are RNA vaccines. You'll have heard of the Oxford AstraZeneca vaccine, which is being used in this country, which is a vector vaccine where the RNA for the spike protein is taken inside the vector, a harmless virus which carries it into the body. But also the Russian Sputnik V system works on the same principle. And the Janssen vaccine, which is just being approved at the moment, also works on the same principle. It's a vector vaccine. Interestingly, the vaccines that have taken longer to develop are the ones by the more traditional methods. And there is the Novavax vaccine, which is a purified form of the spike protein from the outside of the virus. And also there's very promising results from this more traditional method, which is inactivated viruses, and the Sinovac virus, the Chinese virus, and the Valneva virus are both using this particular principle. So a quick reminder of what is the principle of vaccination. This graph shows on the back axis at the bottom, the x-axis time, and on the vertical axis, the antibody response. If you vaccinate at the beginning of particular procedure here, there is what's called a lag period when nothing happens. And then after a few days, you start to get an antibody response. It's called a primary response because it's the first response. And then if you get an infection or a second dose of a vaccine, you get a secondary immune response. And the characteristics of this immune response is that there's a shorter lag phase, less time between the activation and something happening. There's more antibody. The antibody is more effective because it is of higher affinity, and the production of the antibody is extended over months. The other thing that's really important on this graph at the bottom is that after the primary vaccination, memory cells are formed. And there are two types of memory cells. One are called the memory T cells. T cells are involved in getting rid of virally infected cells. And the other type are the memory B cells. B cells are the forerunners of the antibody producing cells. And actually, this particular feature, the formation of memory cells, and it's important, is often much underestimated, at least in the popular press. So what do these antibodies and T cells actually do? Well, the antibodies recognize antigen on the outside of the virus. In the case of SARS-CoV-2, it's the spike protein. And they stop infection of cells by preventing virus attaching to the cell surface. They also promote destruction of the virus, even if it has infected a cell. So a cell that's been infected with a virus that has an antibody attached to the outside can sort of send that virus off down pathways where it is destroyed inside the cell. In addition to that, in the blood, in the serum, the attachment of antibody to the outside of virus causes it to be taken up by what are called phagocytic cells in different parts of the body. But phagocytic cells are effective at destroying virus. A point that's often missed is that antibodies decline naturally over the course of a few months. So there was much debate early on with people saying, oh, but the antibodies are going away. Yes, we always know that antibodies go away. They decline naturally. However, the critical thing is that memory B cells, the ones that will produce the antibody and can produce the antibody again, may persist for many years. And then you've also heard about the T cells. T cells are different in that they recognize not whole proteins, but they recognize fragments of proteins which are on the surface of infected cells. And that protein might be the spike protein from the outside of the virus, but it might be one of the sort of internal proteins from the virus. So the T cells are potentially recognizing a lot more different things. And a T cell can signal to an infected cell to commit suicide. And if a cell's committed suicide, then the virus can't replicate inside it and you're controlling the infection. And like the memory B cells, the memory T cells can persist for many years. So if we go back to our pictures of the virus vaccines here, we can see that the Novavax, the AstraZeneca, the Sputnik, the Janssen, the Pfizer, and the Moderna are all looking at spike protein. And therefore, really, they will have to be adapted to any changes that occur in the spike protein. These ones against the whole virus look not just at the spike protein, but also against many of the internal proteins again. So they will be inducing a wider range of immune response, and potentially they will be activating T cells as well as B cells. And it may be that these kind of inactivated viral vaccines may need less tweaking in response to viral variants. So the vaccines available in phase 3 trials, as we've said, the Oxford, the Sputnik, and the Janssen are all vector vaccines. The Sputnik has 2 different vectors on the first and the second dose. There's a certain advantage to that because what you want is the immune response to concentrate on the spike protein itself and not to have a strong immune response against the vector, because that's not particularly useful. So there may be advantages in mixing vector vaccines on subsequent doses, and trials are going ahead at the moment to look at whether that is actually true. The Janssen vaccine is effective on 1 shot. Now, whether that actually means it's better on 1 shot, or whether it means that the people at Janssen saw that the Oxford AstraZeneca was pretty effective on 1 shot and therefore stuck with that so as to get their trial through quickly, I'm not quite sure. But certainly we know that the other vaccines, the Oxford AstraZeneca in particular, are very effective even with one shot. The Pfizer and the Moderna, as we've seen, are inducing production of the spike protein. The Novavax is purified spike protein, and that would need modifying if a variant arose to which the immune response against the spike protein was ineffective. And then we have these two inactivated viruses. So I thought we would have a look at what is meant by viral variants. And this diagram is a sort of family tree of viruses, starting from December down at bottom left, progressing through to the end of February at bottom right there. So that's a time course. And this is a family tree. And each one of these spots is a virus that's had its genome sequenced. And you can see that there's been a huge amount of variation. So when people say there are a huge number of variants, this is what they mean. There are huge numbers of variants here. And I've just picked out some of them on here. For example, this group in the center, which is red, is the Kent variant, which was first spotted around about, you can see about last August. And then at the top there, we have in the orange, we have the South African variant. And this sort of dark red group in the middle, sort of lower here, is the Brazil variant. Now, you can see that some of these original ones, these blue ones, are sort of dying out. They're much less common, but they are being gradually replaced by these sort of South African, Brazilian, and Kent strains. So we can see that the virus is evolving. But it's not all variants that really concern us. It's what are called the variants of concern. And the reason they might be of concern is because they have an increased rate of transmission. We know that that is certainly true for the Kent variant, the South African, and the Brazilian variant. Another problem is the possible ability to evade an immune response, and the immune response might have been produced by a previous infection or vaccination. For example, the Brazil variant was first spotted when it became apparent that one or two people in Manaus in Brazil had developed a second round of coronavirus infection, and it turned out that it was the Brazil variant that was causing their second infection. It doesn't happen in everybody, but it can happen. Another thing of concern is the ability to avoid detection by our PCR testing. That's obviously inconvenient from the point of view of controlling the infection. John mentioned therapeutic antibodies. These are sort of individual reagents that may be able to stop the virus infecting the cell. If the new variants can evade the action of these antibodies, then that's potentially a problem. Finally, of course, there's the increased ability to cause serious disease, hospitalization, or mortality. And there's a note at the bottom here that increased transmission or evading the immune response are clearly of an advantage to the virus. But interestingly, number 5, which is the increased ability to cause hospitalization or increase mortality, is of serious concern to human beings, but may not be of an advantage to the virus. So if a virus can effectively lay low in the population, so we take little notice of it, like most coronaviruses, then it's not of an advantage to the virus. So an increased rate of transmission does not necessarily mean increased hospitalization. Having said that, we do know that the Kent variant does cause an increased rate of hospitalization, but that's not a necessary corollary. Now, what do we actually mean by variants or mutations? Well, this refers just to the spike protein and some of the variants that have turned up, one from Kent, as I've mentioned, the so-called British variant, the South African variant, and the Brazilian variant. Now, what does a variant mean? Well, a variant has a collection of changes in the structures of its proteins, and proteins are made up by amino acids, And that means a change in individual amino acids. So, for example, if you take variant, this variant here, the Kent variant, one of its amino acids, number 501, has changed from being N to being Y. And that is a change in the receptor binding domain, the part of the virus that actually attaches to the receptor on the cells. Now, it turns out that a number of these viruses, variants, have all independently developed that particular mutation, N501Y. You can see it in the South African one, you can see it in the Brazilian one. And that one is associated with an increased rate of transmission. Initially, the Kent variant did not have this particular point here, E484K. This change arose independently in the South African and the Brazilian lineage, and it helps the virus to evade the immune or part of the immune response. There was a recent variant arose in Bristol, which is a sort of modification of the Kent virus, and that has independently taken on the E484K mutation. And this indicates that there is convergent evolution among some of these viruses, that there are particular changes that they can make which will increase their transmission rate or increase their ability to evade an immune response. Now, viral variants will get around the place, and I looked up this about a week ago to see where the Brazilian strain is. We know that there's one or two in the UK, but it's also prevalent, it's present, but not prevalent in parts of Europe. So viruses do get around. And then finally, I wanted just to show you a little bit of data which addresses this question of what actually causes a virus to mutate in a way that can evade an immune response. And in this experiment, which was done with viruses which had mutated in different ways, so there is the standard virus, let's call this mutation 1 and a different mutation here. These, and this at the bottom shows a representation of what the spike protein looks like. You can see that against the standard virus, this is a neutralization curve, that all of these antibodies listed here, C121, C135, and C144, are effective at neutralizing the regular virus. But when a mutation takes place, this one here, you can see that only the C135, the green line, is still effective against it. Now, if one of these antibodies was being used therapeutically, it would mean that C121 or C144 had suddenly become ineffective against this variant, whereas this monoclonal antibody, the 135, would still be effective. If you look at this graph on the right, different variant, it's exactly the opposite. And the reason for that is because these antibodies are binding to different parts of the spike protein. And if one part of the spike protein changes, it means that an antibody may not bind to it, but antibodies can still bind to other parts of the protein and still neutralize the virus. So running on to more or less the last slide here, I know time is going on. I just wanted to show you this because we're looking at convalescent plasma here. So two convalescent plasmas. So these are convalescent plasma 47 and convalescent plasma NY. We'll look at those two at the top. You can see this is their ability to neutralize a virus on the black line. And if you take a look at the bottom, the bottom left graph down here, you can see that this serum is able to effectively neutralize the regular virus in black, but it's also able to neutralize a mutant virus in orange. It does exactly the same. Whereas this convalescent plasma bottom right from New York is not able to neutralize the neutralize this particular sort of orange variant here. The opposite is taking place in the top left and the top right for This particular virus here, the convalescent plasma 47 for this particular variant here, this one in sort of a purpley blue color, it's just less effective against it. So what does that mean? We know that antibody against the spike protein can prevent infection and reinfection. We know that T cells destroy infected cells and reduce virus spread and disease severity. Current vaccines mostly include spike protein only, but some upcoming vaccines are based on the whole virus and therefore may be more comprehensive in the kind of immune response they produce. We know that each variant has a number of mutations which affect different components of the virus, but only a few of them, which we've identified, Brazil, South Africa, and Kent variant, are variants of concern. We know that some variants can partly evade a previous immune response, but looking at those convalescent plasma, we know that there are different degrees of evasion between different individuals. So for one individual, a variant might be seriously likely to produce a reinfection, but for another individual, that variant may have little consequence. And we know also, which is very good news, that the vector vaccines, the mRNA vaccines in particular, can be rapidly adjusted to respond to the appearance of the new dominant variants of concern. So I'll stop sharing there and we can, I think, probably go over to some questions, Rachel.
Yes, exactly. Thanks very much, David and John, for two really interesting discussions about treatments and vaccinations. So we're going to go over now to some questions which people have been submitting during the session so far. So I'm going to start with a few questions that we've had in about treatments. So there's been a couple of questions from, I think one's come in from Joanne, asking about the timing of treatments and whether perhaps we should be changing the advice that we give to people about when they seek help for treatments, if the treatments are being given when patients are already too sick.
We could do that, but the trouble is that this disease progresses very, very rapidly. Within a couple of hours, you can go from walking around to not being able to breathe properly. So I'm not sure that that's always going to be the case. Some people it takes longer, but there are cases where it's just horrendously rapid, the onset. But yes, anything that we can get in there more quickly. So some of those blocking antibodies, they look like they might have potential to early on. But as I said, some of the stuff that works very nicely in addition, you would imagine could have an effect, is often just too late for it to really have an effect. So I think an antibody approach probably is going to be the way to go. And I don't know, any test that can try and pick it up sooner, if such a thing can exist.
Thanks, John. So actually, on the subject of testing, we have had a question from Joanne about when they're doing the testing now for different variants. For example, there's been examples of mass testing for the South African variant in different areas of the country. What exactly are they looking for when they're testing for those different variants in those tests?
Okay, shall I take that particular one? To be at the basic test, the PCR test, essentially is designed to pick up as many variants of the virus as possible. And what they use in those tests are what are called primers, which basically look for a piece of virus's genetic information. And they choose the primers to recognize pretty well every variant of the virus. A lot of the screening, and especially the sort of close screening in particular areas where they think there might be an outbreak of a particular variant, they then go on immediately to sequence it. In other words, to try and see exactly what has happened and exactly whether they do have the variant or the or a change in the virus by sequencing it. And this can be done very rapidly these days. It is possible to make a PCR test which specifically targets one variant or the other so that you could actually screen by that. But that is not generally being done at the moment.
Okay, thanks for that one, David.
And I should add that they're doing some trialing at the moment, looking at doing PCR tests on sewage outflow in cities, which seems to be really working very well. I heard something on the radio about that yesterday, and they're able to pick up an increase in cases a couple of days before it actually happens, just by checking that, and they can pick up about one case in 10,000 by that testing. And as David said, then they can send it away for sequence testing, so they know exactly what mixture of variants are in that population. So it can give you a little bit of a heads up as to what's coming. Get about 2 days notice.
Okay, thanks. Thanks for that, John. We've had a question about people who have already had COVID. So people that have already had COVID should have antibodies, have produced antibodies against COVID. So do they still need the vaccine? And if they do need the vaccine, should they be put to the back of the queue for vaccination?
Okay, I'll try that. It's my thought is that if you've had a natural infection with COVID, you should be at least as well protected as if you have the vaccine, because not only have you encountered the spike protein, but you have also encountered the other components of the virus, and you may well have induced some immunity against those, which is likely to be advantageous. Now, that's from a theoretical point of view. From a practical point of view, should those people go to the back of the queue? First of all, quite a lot of people will have had a COVID infection and a vaccination, because on the rollout of the vaccine, the best way to do it is to get everybody over 80, everybody over 70, everybody over 60. They don't want to have detailed discussions over whether you may or may not have had the vaccine, the infection before. The thing to do is get you to have the vaccination. It certainly won't harm afterwards, and it may well help as well. And if there are variants, a tweaked vaccine may indeed be necessary or advantageous. So I would think when it comes to who gets it, a lot of it comes down to the practicality of it. You know, you might say, we want to immunize bus drivers or something like that, but actually organising a program to immunize bus drivers or someone like that, as opposed to a particular age group, suddenly becomes very difficult.
Great. Okay, let's move. I'm just looking through the list of questions here that people have been sending in. We've got some really great questions. So we've had a number of questions about the different components of the different vaccines. So one here about the Novavax vaccine, which has some plant-based components in it, and some questions about what those different components might be doing.
Well, I know there are quite a few of those, the vector-based ones, they contain polyethylene glycol, or they've got liposomes in them. That's just there to protect the RNA. RNA by itself, sort of naked RNA, won't last very long in the body. It gets rapidly degraded. You need it to survive long enough in the bloodstream to be able to get into cells. So they will put some components in there that help to stabilize it, stop it being just taken up by macrophages and lost from the circulation. So I imagine that's most of what's in there, and the main one I can think of is PEG.
I don't think I can add anything to that. I don't know specifically what the composition of the Novavax virus is, but I would imagine, as John says, that it is some kind of, if there is that in there, it would be some kind of element of a carrier.
Yeah, and the other ones, I mean, they tend to have adjuvants in there as well, don't they, David? I think so. I'm not sure what a typical adjuvant is these days.
We do know that the Valneva virus, which is the inactivated virus, has two components in. One is alum, which is in many vaccines, and another is something called CpG 1018, which is a kind of nucleic acid component that sort of jollies up the immune system. That's essentially what adjuvants do.
Great, thanks both. So I've got a question come in from Patrick. It says, what is the scientific reason for delaying the second dose of the vaccine, and how might that affect the efficacy of the first dose and thus the overall course?
Okay, so the reason, as you know, for delaying, the scientific reason for delaying the second dose of the vaccine is entirely pragmatic, that it's better to have your grandmother and your grandfather immunized with one dose each than to have your grandfather immunized with 2 doses and nothing for your grandmother from a public health point of view. So that's entirely pragmatic. But even before that, when people set up the vaccine trials, they set them up as in, let's go for what we think is going to be the most likely to work, because in June, people didn't know if these things would work or not. So they said the most likely thing to work at all is to maybe have 2 set 3 weeks apart. Looks quite likely. From an immunological point of view, maybe having it a bit later makes sense, because what happens is a slightly later reactivation allows the immune system to develop better and higher affinity antibodies prior to the boosting of the second dose. So we've always known that, but from a pragmatic point of view, they didn't want to waste time waiting 12 weeks to see whether 12 weeks is better than 3 weeks, because they wanted to get the vaccine out. So there are good reasons, both from a public health point of view, spreading the vaccines, and from an immunological point of view, actually getting a better quality of response for having some delay in the system.
Thank you. Thanks very much, David. I've got a question about mutations in the virus. So Rainer's asking, with the mutations of the virus being global, do you see that the vaccine will have to be adjusted and delivered in different parts of the world, or will we need to have global vaccine rollouts over and over again for different versions of the vaccine?
Okay, so yeah, very good question. I think we will probably have to have new vaccines against the different variants. And the way we do this with flu at the moment is in the Northern Hemisphere, we see what's circulating in the Southern Hemisphere in the sort of summer. We make vaccine against that, and then that's what's distributed in the Northern Hemisphere. Part of the problem is if you completely suppress a round of infection, as has happened with flu this year, you don't know quite what your target is. So we don't know what the dominant strain of flu in the Southern Hemisphere is this year. And therefore, it's more of a guess as to what will be next year's flu vaccine. The same kind of problem may arise with coronavirus vaccines, but I think probably in the first 2 or 3 years, until the virus, as I suspect, will kind of settle down within the population, that it will be a process of catch-up.
Thanks, David. Okay, I've got one final question that's come in. We've just got a couple of minutes left, so we'll just do this final question. So do you see any potential end to COVID, or do you think it will turn out to be similar to the flu with things like yearly boosters?
I think it is likely to be that we are not likely to see absolutely the end of it. And I think we may have yearly boosters until such time, if it occurs, that it's so benign that we're not too bothered about it like other coronaviruses. There was one question that came in, incidentally, Rachel, by on the thing.
Yes, sorry, we'll just do that last one. It was right at the top and I missed it, I'm sorry. So it was a question about how will vaccines like the Chinese Sinovac vaccine and other international vaccines get approval for countries like the UK?
Okay, so we had a bit of notice of this one, so thank you for that question. the short answer is that they'll be approved or not approved in exactly the same way as the Pfizer, the Moderna, and the Janssen vaccines, and any others that we are looking at. Obviously, there'll be a lot more data from real-world activity going on. I suppose as far as Sinovac is concerned, the question is whether bearing in mind that it seems to be effective and it's being distributed across Africa and many other places, whether the Chinese will want to go through a whole series of submissions to the UK regulatory authorities to have it approved here when they've got lots of other useful things to do with that vaccine in other parts of the world.
Thanks, David. Okay, so I think, unfortunately, we've run out of time in today's session. It's 1 o'clock now. So thank you, everybody online, for submitting all of your questions to our experts today. And a big thank you to John and David for a very interesting session. And thank you all for coming, and enjoy the rest of your day.
Thanks for inviting us.
Thank you.
Thank you very much.
Okay.
Bye-bye, everybody.
Bye.
Bye, and keep well.